In this last lecture of the module, we will discuss phase changes, specifically phase diagrams. Well, what's a phase diagram? A phase diagram is a visualization technique intended to summarize what phase a particular compound would be in under any particular combination of pressure and temperature. What we have here is a phase diagram of water. We'll look at some specific things about this diagram, but let's just look at it in general. What we have here on the x-axis is temperature in degrees Celsius, on the y-axis pressure in atmospheres, and we have different regions where solid water or ice, liquid water or water vapor exist. In other words, the particular pressure temperature combinations where solid, liquid, or gas would be prevalent. So under these combinations of temperature and pressure, you'd expect to see ice. Under these general conditions of pressure and temperature, you'd expect to see liquid water. And under these particular conditions of pressure and temperature, you'd expect water to exist in the gas phase. So let's look at some specific things about this phase diagram. The first thing is you'll notice that both the x-axis, the temperature axis, and the y-axis, the pressure axis, are not drawn to scale. The markings are not evenly divided. This actually will work to our benefit. Certain temperatures and pressures are marked for very specific reasons. We'll cover all of these soon. A phase diagram is constructed using experimental data obtained in a closed system. However, these diagrams are still informative for those of us who do experiments in open systems. We generally do experiments in a laboratory that's open to the atmosphere. A black line separates any two phases. So in other words, here is the solid liquid line, here's the liquid gas line, here is the the solid gas line. Specifically, what these lines are particular pressure temperature combinations where the two phases can exist at equilibrium. So if we follow the solid liquid line here, any pressure temperature combination on this line is a possible spot where solid and liquid water can exist in equilibrium. Along the liquid gas line are conditions of pressure and temperature where where liquid and gas can exist in equilibrium. And this line, particular pressure and temperature combinations where solid and gas can exist in equilibrium. The triple point, which is marked on the diagram here, is where all three of these lines meet, and it's the one combination of temperature and pressure where all three phases can exist in equilibrium. For water, the triple points at 0.0098 degrees C under a pressure of 0.00603 atmospheres. The critical point, which is also marked on the diagram here, it's at the end of the liquid gas line, or it's where the liquid gas line seems to disappear on the diagram, is the combination of pressure and temperature where the phase boundary between liquid and gas seems to suddenly vanish. For water, the critical points at 374 Celsius and 218 atmospheres. We'll return to talking about the critical point in a few minutes. If you insist on believing the world is flat, you might think of the critical point as where you would fall off the edge. Let's attempt to highlight some specific temperature-pressure combinations noted in the phase diagram of water, and I've used some color coding here. First of all, You're well aware that the normal melting point of ice is 0 degrees C. And remember, when we use the word normal melting point, we mean the melting point under normal atmospheric pressure, or 1 atmosphere of pressure. So if we start at 1 atmosphere of pressure and we follow this red dotted line over to the solid liquid line and follow that down to the temperature axis, we see that temperature is 0. The normal melting point of water is 0. Likewise, the normal boiling point, which would be the point on the liquid gas line where we have 1 atmosphere of pressure. If we go down from there, the graph would read 100 degrees C. Of course, that's the normal boiling point of water. The triple point, as we discussed before, is at 0.00603 atmospheres and 0.0098 degrees C, marked by the green dashed line and that big black dot. The critical point, again mentioned previously, is the point at which the pressure is 218 atmospheres at a temperature of 374 degrees Celsius. So 374 is referred to as the critical temperature of water, and the 218 atmospheres is referred to as the critical pressure of water at that critical temperature. Now let's see if the phase diagram of water can be used to make predictions consistent with our everyday experience. So I've reproduced the phase diagram to the right here. To do this, we can take kind of a journey across the phase diagram from low temperature to higher temperature at a constant pressure. And we're going to choose a constant pressure of 1 atmosphere, normal atmospheric pressure. So we'll start from very low temperature under normal atmospheric pressure and go from left to right to very high temperatures. And we can see what the diagram will predict, and if that makes sense to us from what we observe in everyday experience or in the laboratory. So I've marked point x1 on our dotted line, and x1, you can see, is at a temperature less than 0 degrees C under normal atmospheric pressure, and the phase diagram predicts that water would exist as a solid under these conditions. That seems pretty reasonable. How about at point x2? Well, at point x2, we're right on the solid liquid line, so we've increased the temperature to 0 degrees C. What's going to happen there? Well, remember, that's the pressure temperature combination where solid and liquid water could exist in equilibrium, but just as importantly, if we're increasing the temperature from left to right, it's where the solid will melt to a liquid. So that would be our normal melting point, 0 degrees C. At point x3 on our journey, we're within the liquid water area of the diagram. Does this make sense? Well, we're under still a normal atmospheric pressure, and we're at a temperature between excuse me, 0 and 100 degrees C, and so we would expect water to exist in the liquid phase. Let's continue our journey. We're now at point x4, and we've raised the temperature to 100 degrees. Well, what happens to liquid water when we raise the temperature to 100 degrees under normal atmospheric pressure? The water begins to boil. So we're at the boiling point of water, and liquid is being turned into a gas. If we continue to heat or increase the temperature, then point x5 is within the gas region of the phase diagram. It makes sense. We're now at greater than 100 degrees. We've turned the liquid into a gas. This makes perfect sense from our everyday observation. If we continued heating and say raise the temperature even above the critical temperature here, you might ask, well, what's going to happen there? Well, according to the diagram, the water stays in the gas phase, and what we really have is just some very hot gaseous water. Now let's look at more on this phase diagram on the next slide. As promised, we want to return to discussing the critical point on this diagram and some details about that. As the term implies, the critical point is the particular temperature and pressure combination marked on this diagram. And you might say, why is it the critical point? Well, remember we said this is where the liquid gas line seems to disappear, and we said beyond the critical point, the phase boundary between liquid and gas seems to disappear. So let's look a little more closely at what's going on. Now, to do that, we might take yet another journey across our phase diagram, and this time we're going to take this journey under a very high pressure. In fact, we're actually going to be slightly above the critical pressure. So I've marked a spot at 220 atmospheres on the y-axis, and we're going to take our journey from left to right, increasing the temperature under this pressure. And we want to look at what the diagram would predict would be happening. So let's look at point x1 in the diagram. And this would be a temperature that's significantly less than 0 degrees. Here's 0 degrees, so we're significantly less than 0, under a pretty high pressure, and the diagram predicts that water would exist as ice. Well, we'd have no reason to argue with that. That seems perfectly reasonable. How about at point x2? Well, here, interestingly enough, we're crossing the solid liquid line. The temperature is still below 0, because remember 0 is over here. We're still at a very high pressure, and the diagram predicts that the ice would begin to melt. Okay. How about point x3? Well, at point x3, we're at a temperature between 0 and 100, still at this very high pressure, and the diagram predicts that water would exist in the liquid form. We have no reason to argue with that. Now I drew in point x4 and x5 here at the same time, and let's look at what might be going on there. This is where it could get a little strange. Note that at point x4, we are approaching the critical temperature, and remember at the critical temperature, we're going to see not only this liquid gas line disappear, we're going to see the phase boundary between liquid and gas disappear, but we're not quite there yet. We're just short of that critical temperature, and we're still at a very high pressure. So it's probably safe to say, and I think the diagram kind of predicts here, that water would still be in the liquid phase. If we keep increasing the temperature so that now the temperature is above the critical temperature, we're going to go over to point x5. The diagram predicts that we no longer have either a liquid or a gas, but actually what it's saying is that we have a new phase, and it's actually called a supercritical fluid, which I've marked here as a rectangular box, kind of a purple color, on the phase diagram. Now we might reasonably expect the properties of supercritical water, in other words, water in the form of a supercritical fluid, to be somewhat intermediate between that of liquid and a gas, because remember we said the supercritical fluid is a fluid that's formed when the phase boundary between liquid and gas just seems to disappear. We still have a fluid, but it doesn't seem to be a liquid or a gas. So it might not be unreasonable to assume that the properties, some of the properties of this water in the supercritical state would be intermediate between that of liquid and gas. Well, we can see that this is true in at least one case, because if you compare the measured densities for liquid water and gaseous water near but not at the critical point. Now these would be experiments that would not be very easy to do, but what we're saying here is that if you could measure, and this has been done, the densities of the liquid and gas forms of water near the critical point at high pressures and high temperatures, and compare those densities to the densities of actual supercritical water, you'd find that the reported density of liquid water is 0.52 grams per cubic centimeter. That of gaseous water is 0.18 grams per cubic centimeter. This makes sense. Gas less dense than the liquid. The reported density of H2O(SC), that means supercritical water, interestingly, is 0.32 grams per cubic centimeter, which is pretty much between the density of liquid water and gaseous water. You might say, what's the point of producing water in this weird supercritical fluid state? It turns out that supercritical fluids can show completely new and useful properties compared to the liquid or gas forms of the same substance. One additional feature of the phase diagram of water that we want to point out here is that the line dividing the solid and liquid phases is left leaning. It leans to the left. So let's see why that might be important. What it implies is that solid water or ice has a lower density than liquid water. Well, if we think for a minute, we remember that ice floats on water, and we mentioned before that ice is less dense than water because when water freezes, the presence of hydrogen bonding and the geometry imposed by these hydrogen bonds makes the structure of ice much more open than that of liquid water, and so ice is less dense than water. Let's look at some experimental data. Believe it or not, it's possible to produce something called supercool liquid water at temperatures below 0 degrees. Under 1 atmosphere of pressure, so this would be right here on the graph on the y-axis, and minus 10 degrees, so we'll have to guess where that is, let's say about here. Under very tightly controlled experimental conditions, it's possible to trick water into staying in the liquid form. If the density of that liquid form of water at minus 10 is measured, it's measured to be 0.9982 grams per cubic centimeter, while ice under those same conditions, 1 atmosphere of external pressure, minus 10 degrees, is only 0.9187 grams per cubic centimeter. So yes, ice is indeed less dense than water. It seems reasonable that increasing pressures would favor the more dense phase, in this case the liquid. Therefore, we would expect that increasing pressure would lower the freezing point of water. You can see here that at, say, this temperature here, which is just less than 0, if we increase the pressure, if we go to high enough pressures, we can see that we go from the solid to the liquid phase. In other words, as the pressure goes up, this line that's leaning to the left says that the melting point of ice, which is right along this line, keeps decreasing. It's moving to the left. This results in this left-leaning line then shows us that the melting point decreases with increasing pressure. And it also tells us, of course, that increasing the pressure favors the liquid form, the more dense form. The experimental data is not quite as dramatic as what this diagram makes it look. If you go from a temperature, I should say a pressure of 1 atmosphere, where the melting point is 0, and you increase the pressure to a very high 200 atmospheres, which would be just under this 218 here, it turns out that the melting point of ice does drop, not by a lot. It drops by minus 1.52 degrees C. So I've tried to mark that on the diagram here. However, this is a real drop in melting point. Again, remember the temperature and pressure axes here are not to scale. So this particular phase diagram could be exaggerating this left lean. However, the left lean is real, and pretty soon we'll look at these phase diagrams with temperature and pressure axes that are to scale, and we can see what the diagram looks like. It'll look a little bit different, but the phenomenon is real. This line does lean to the left. For now, let's compare the phase diagram of water, which we've discussed in detail, to that of another substance, carbon dioxide. So on the right-hand side, we have the phase diagram of water, which we've been discussing. It is marked up a little more, but it is the same phase diagram we've been working with. And on the left is the phase diagram for carbon dioxide. Now, even though the general outlines of the two phase diagrams are fairly similar, you'll see the major difference here is that this solid liquid line for CO2 is leaning to the right, where it leans to the left, as we've just discussed for water. But there's something else that's drastically different about these two diagrams, and it's that the temperature and pressure scales are completely different. And what I mean by that is that the temperature scales, the temperature in degrees C, the temperature ranges are much different for water. The middle of the x-axis is 0 to 374. The middle of this x-axis for CO2 is minus 78 to only 31. The pressure axes for water seem to go to much higher numbers than for carbon dioxide. So what does this mean? What does the difference in the temperature scales mean for us? Well, first of all, it means that carbon dioxide is predicted to exist as a gas at room temperature under 1 atmosphere of pressure. And I've marked that on the CO2 phase diagram with an X. So in other words, at 1 atmosphere of pressure, which is now here on this y-axis, and room temperature, which I've estimated as a little bit less than 31 degrees C, it's predicted that carbon dioxide will exist as a gas. That's consistent with our everyday experience. However, under the same conditions, water at 1 atmosphere and room temperature is predicted to exist as a liquid. And we know that to be true according to our own experience. Solid CO2, in other words, CO2 that is under pressure and temperature conditions that would put us in this region of the phase diagram, specifically 1 atmosphere of pressure, is predicted to sublime, in other words, change directly from a solid to a gas under 1 atmosphere of pressure as we increase the temperature. So solid CO2 won't form liquid CO2 if you put solid CO2 on your desktop. It goes directly from solid to gas, thus the term dry ice. However, we know that water in the solid form, or ice, under the same pressure as you increase the temperature, will melt to a liquid. And we've got that marked on the phase diagram of water. And as we mentioned at the beginning of the slide, the line dividing the solid and liquid is slanted to the right in the CO2 phase diagram. And what that means is that solid CO2 is more dense than liquid CO2 at the same temperature. So if you picked any temperature here, let's say where my arrow is, and increase the pressure, then CO2 will solidify. And as we discussed, exactly the opposite for water. If you have water in the solid form at a particular temperature and increase the pressure, this diagram predicts water will melt. In other words, it goes to its more dense form, liquid, and CO2, the more dense form, is the solid. Now remember, the X and Y axes on our previously shown phase diagrams were all labeled not to scale. Now the core challenge in depicting these phase diagrams is the remarkably large range of pressures needed to be shown on the Y-axis. If we plot the pressures on the Y-axis in regularly spaced powers of 10, which we'll call a log axis, it is then possible to plot the temperatures on the X-axis in a normal way. The results for both CO2 and water are shown below. Now, you'll see that forcing the X and Y axes into properly and evenly scaled increments, you'll see the temperature is now in even increments on the X-axis, and the pressures are in even increments of powers of 10, in other words, a log axis. It completely changes the look of both phase diagrams. However, they still give the same information as the previously scaled diagrams did. Let me give you an example. CO2 exists as a gas at 1 atmosphere of pressure and room temperature, marked by the X on the diagram. And we know this to be true. So at 1 atmosphere and a little bit above 0 or room temperature, we predict CO2 would be a gas. So this diagram seems to be working just fine. And remember, we said we know that solid CO2 sublimes to gaseous CO2 under 1 atmosphere of pressure as the temperature increases, and that's exactly what this diagram would predict. If we look at the phase diagram for water, we see that water exists as a liquid under 1 atmosphere of pressure and room temperature. If you looked at the scale really closely, you could argue that I missed room temperature here, but give me a break, it's hard to put that X in this little area. And under 1 atmosphere of pressure, we know that solid water or ice melts to liquid water at 0 degrees C. So even though these diagrams look much different than the previous ones because we've scaled the axes differently, they're giving us the same information. Let's look at an example question involving the phase diagram for yet another substance. In this case, we want to talk about methane, CH4, which is the principal component of natural gas. So here's the phase diagram for methane. The temperature scale, of course, in degrees C, marked in even divisions, wide temperature range, and the pressure is on a log axis, as we saw on the previous slide for water and CO2. Let's see if we can answer some questions from this about methane from this phase diagram. Let's estimate the temperature and pressure conditions at the triple point of methane. Well, remember, the triple point is the point where the 3 boundary lines all meet, and we can estimate that at being at around 0.1 atmospheres and a little bit higher, more positive, of minus 200 degrees C. My best guess here was actually 0.2 atmospheres and minus 182 degrees C. You might ask how I could get a number quite that specific from this rather vague diagram. I think I took this diagram, blew it up, printed it out, and used a ruler to get the best estimates that I could. What would be an estimate of the values of the critical temperature and critical pressure? Well, remember, the critical point is at the end of the liquid gas line, and we just have to try to get an estimate for the pressure and the temperature at this point. And my best guess was, of course, between 10 and 100 atmospheres, I guess 60, and a little bit less than minus, I should say a little bit more, a little bit higher than minus 100 degrees, or less negative, I guess minus 82. Now, methane is well known, just by everyday experience, to be a gas under normal atmospheric pressure and room temperature. So what we're going to do is mark on the diagram an X for a normal atmospheric pressure, that's 1 atmosphere, and room temperature, that would be slightly higher than 0 degrees, about 20 degrees, 25 or 20 degrees C. We'll put an X right there, and indeed, the diagram does predict that methane should be in the gas phase. Now, if you start at point X, keeping the temperature at room temperature and just increase the pressure, does it look like we could ever condense the gas to a liquid? And the answer to that is probably not, because it appears that the gas would go to a supercritical fluid. Now, a common way to define the critical temperature is to say that it is the temperature above which you cannot condense a gas to a liquid, no matter how much pressure is applied. Is the result that we found in number 4 here consistent with this definition of critical temperature? So you can see on the diagram here that the critical temperature is about minus 82 degrees C. At room temperature, we are well above that critical temperature, and it appears that no matter how much pressure we put on, we cannot go from a gas to a liquid. We seem to go from a gas to a supercritical fluid. So yes, what we found is consistent with the definition of critical temperature. It's a temperature, critical temperature of minus 82, above which you cannot condense a gas to a liquid. No matter how much pressure you put on it, the gas will go to a supercritical fluid. So our answer to number 5 is yes. Can we estimate the values of the normal melting and boiling points of methane? Well, sure. Remember, the normal melting point would be the temperature at the solid liquid line at 1 atmosphere. My best guess here is also minus 182, because it seems to be the same temperature as the triple point temperature. And what would the boiling point of liquid methane be at 1 atmosphere of pressure? Well, we'll stay at 1 atmosphere and just go over to this liquid gas line. And my best guess here is about minus 162 degrees C for the boiling point. Would solid methane require a higher or lower temperature to melt if the pressure was increased from 1 to 1,000 atmospheres? Well, 1,000 atmospheres is up here, 1 atmosphere is here, and what we're looking at is the melting point along this blue line, and it appears that if we go from 1 atmosphere to 1,000, that the line between the solid and the liquid moves to higher temperatures. So that means that we would require a higher temperature to melt solid methane at the higher pressures. Finally, what phase change would occur if solid methane at minus 240 degrees C was heated to minus 160 under a pressure of 0.01 atmospheres. Well, 10 to the minus 2 is 0.01 atmospheres. Let's find minus 240 degrees C. The scale is a little hard to read here. If this is truly 0, this would be minus 20, 40, 60, 80, 100, minus 120, 40, 60, 80, 200, minus 220, minus 240. So we're going to start right here, and we're going to stay under that pressure and increase the temperature to minus 160, which would be over here. It appears that we're simply going to sublime the methane from the solid to the gas form. So you can see how we can use the phase diagram of any substance to make predictions about what would happen as we change the conditions of temperature and pressure under which that substance exists.